To practice with calculus of polar coordinates, I'm going to update the problem that we looked at just for the introduction to polar coordinates video. So I've just kept the slop that I made as scratch work for that problem, where we just plotted 3 minus 2 cosine theta. And this time I'm going to ask for the area between this curve, 3 minus 2 cosine theta. I mean, it's drawn, might as well use it, right? The area between that curve and the curve r equals 2. Now you want to remember that in polar coordinates, r equals 2 says, hey, go find me all the points that have a distance of 2 from the origin. Well, that's a circle. And that circle is going to look like this, sort of. And so the area between the blue curve and my new circle is this cusp right there. And so what we're going to need to do is find those 2 points of intersection, because those are going to be the bounds on our integral. If you've seen the notes already, I hope you're watching these videos after you've looked at the notes. The generic formula for the area inside a polar curve is the integral of 1/2 times the polar function squared, where the limits on theta are the starting and ending values of theta that sweep out the area that you're interested in. You do the same thing with this area formula as we did in rectangular coordinates. If we want an area in between two curves, we'll take the area inside the larger one and subtract away the area inside the smaller one. So we'll do the integral of 1/2 of the blue curve squared minus 1/2 the red-ish curve squared, once we've discovered these 2 points of intersection, because those are going to be our limits. To find the points of intersection, we just want to ask, where does 3 minus 2 cosine theta become equal to 2? Well, if we add 2 cosine theta to both sides and then subtract 2, this is the same as looking for 1 equals 2 cosine theta, which is also the same as looking for cosine theta equals plus or minus pi over 3. And that's kind of consistent, right? Let's get a different color here. Array of minus pi over 3 and array of plus pi over 3 from the origin seem to be reasonable. And then again, we're looking for that. So the final expression for area that we want would be the integral from minus pi over 3 to pi over 3, and then 1/2 times the outer function squared minus 1/2 times the inner function squared, which I can group together like this. Like so, and then at this point, blah, 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 it'll get done. You can multiply out the 3 minus 2 cosine squared, collect some constants, factor out the 1/2, etc., etc., or again, because the construction of the integral is the important thing here, if you take this and just go to tech and say, hey, what's the final value of this integral, that's fine as long as you've reported this integral correctly, and then you give the source of the computation of it. You can leap from the integral to the final value. That's fine. Okay, for our next example, we're going to find the arc length of the function 6 sine theta plus 8 cosine theta, where theta, not t, theta, there we go. Good thing that's an easy fix. Theta goes from 0 to pi. As you found in the notes, the generic arc length formula in polar form is kind of a mess. It's a big fat square root, and it's the square root of r squared, or your function squared, plus the square of its derivative. So I'm going to build up to this interior. I'm not going to build the integral and shake it out as a whole thing. I'm just going to do the parts and then see what those parts look like and then create the integral. So here's r. R equals 6 sine theta plus 8 cosine theta, right? And then r prime is 36 cosine theta minus 36, no, I'm not squaring it yet, I'm getting ahead of myself, is 6 cosine theta minus 8 sine theta. So r prime squared, now we're going to have 36 cosine squared theta minus 64, plus 64 sine squared theta, and don't forget those cross terms. 8 times 6 is 48, 2 of those is 96, so minus 96 sine theta cosine theta. And then let's also generate r squared itself. Well, that'll be 36 sine squared plus 64 cosine squared, and then cross terms of plus 48 sine cosine, so 2 of those is plus 96 sine theta cosine theta. And so this interior of the integral, which is r squared plus r prime squared, well, 36 cosine squared plus 64 cosine squared, that's 100 cosine squared altogether. Similarly, 100 sine squared, and the cross terms are gone. And even better, that's 100 cosine squared theta plus sine squared theta. Now, don't panic and say, oh my gosh, I'm going to have to do a square root and start doing substitutions to get this integral done. Always keep an eye out for trig identities, because this is just 100 times 1. And so the square root of r squared plus r prime squared is just the square root of 100, which equals 10. All right, so you were looking at this formula, and you were looking at that equation for our curve and going, oh my gosh, this is going to be terrible. Well, it's not terrible. The arc length altogether is the integral from 0 to pi, the limits were given to us, times this thing we just built, 10 d theta. Easy as that. And that is 10 pi. Now, here's a trick that's not always going to work, but sometimes it does. We could have figured out this answer just by knowing a little bit of geometry. It's good to be able to do the formulas, but what if I were to break this function down and just look at 6 sine theta? That happens to be a circle that sits above the x-axis with a radius of 3. And so as theta sweeps from 0 to pi, we generate that entire circle. The circumference of that circle is going to be 2 times pi times the radius, which is 6 pi. The other half of this function, r equals 8 cosine theta, that just happens to be a circle that sits on top of the x-axis, and it has a radius of 4. So as theta goes from 0 to pi, we sweep out the top half of that circle. That half of a circumference is 2 pi times the radius times 1/2. And that is 8 pi times 1/2, and that's 4 pi. So the net circumference of these two is the sum of those two things. And there's also how we could get our 10 pi.